Have you ever looked inside a piece of electronics and wondered what makes it all work? Well, today we're going to demystify one of the most important little components in that whole world, the operational amplifier, or as pretty much everyone calls it, the op-amp.
All right, here's our game plan. We're going to start with what this amplifier on a chip actually is. Then we'll get into its anatomy, figure out how to tame this wild beast using feedback, see some really cool examples of it in action, and finally, I'll walk you through how to pick the perfect op-amp for your own projects.
Okay, first things first, the amplifier on a chip. What is this little magic box, and what's its whole deal? Let's crack it open and see why it's so critical to, well, almost everything.
So at its core, here's what an op-amp does. It looks at two different voltages, finds the tiny, tiny difference between them, and then it amplifies that difference by a huge amount. You can think of it like a super-powered magnifying glass for voltage, turning a little whisper of a signal into a really loud shout.
So what's the secret sauce here? What gives the op-amp its superpowers? It's not just about being loud. Let's dig into the ideal characteristics that make this thing such an amazing and predictable tool for engineers.
You're going to want to get familiar with this little triangle. You'll see it absolutely everywhere in electronics. It's the symbol for the op-amp. See the two inputs? One is the inverting input with the minus sign, and the other is the non-inverting with the plus sign. And then there's just that one single output. So let's start with its raw, incredible amplifying power.
Right out of the box, with nothing else attached, an op-amp has something called open-loop gain, and it is just massive. We're talking over 100,000, sometimes even millions. It's like having a microphone so sensitive that a pin dropping a mile away would sound like a jet engine right next to your ear. That's the op-amp in its raw state.
And here are two more of its ideal qualities. It's got this super high input impedance. That's like having perfect hearing. It can listen to a voltage signal without disturbing the circuit it's listening to at all. On the flip side, its output impedance is incredibly low, which is like a powerful stereo system that can drive speakers without breaking a sweat. It's this perfect combo of a super sensitive sensor and a super powerful source.
But, of course, there's a catch, right? That incredible gain really works best for signals that aren't changing too fast. You know, low-frequency stuff. As your signal starts getting faster and faster, the amount of amplification you get starts to roll off or decrease. This trade-off between how much you can amplify and how fast your signal is, that's a really key thing you have to keep in mind.
So, what we have is this incredibly powerful but kind of wild amplifier. I mean, a gain of 100,000 is just, it's too much for most things. So the big question is, how do we tame this beast and make it do something useful for us? And the answer is this absolutely brilliant idea called negative feedback. We take a little piece of the output signal and we feed it back into the inverting input. What this does is create a self-correcting loop. It's exactly like cruise control in your car, which is constantly tapping the brakes or the gas to keep your speed perfectly steady. This feedback loop keeps the op-amp stable and predictable.
At the end of the day, what we're doing is trading all that massive, unstable raw power for a smaller but perfectly controlled amount of gain. By adding a couple of simple components like resistors into that feedback loop, we can dial in the exact amount of amplification we want. This is what turns the wild op-amp into a precise, reliable, and incredibly useful tool.
Okay, so now we know the rules of the game, right? We've got high gain, these ideal input and output characteristics, and we have the power of feedback. So let's look at some of the most common circuits you can build with this thing. Think of these as the fundamental recipes in the cookbook of analog electronics.
First up, we've got the simplest one, the voltage follower. You literally just connect the output directly back to the inverting input. This gives it a gain of exactly 1. So you might be thinking, wait, what's the point of an amplifier that doesn't amplify? Well, it acts as a perfect buffer, kind of like a bouncer at a club, protecting a weak, sensitive signal from being loaded down by whatever comes next in the circuit.
Next is the real workhorse of the op-amp world, the inverting amplifier. This circuit boosts your signal and it flips it upside down. A positive voltage in becomes a negative voltage out. And the best part? It's so simple. The gain is just the ratio of those two resistors, R2 divided by R1. That's it. You want 10 times the gain? Just make R2 10 times bigger than R1. Easy.
And right alongside it, you've got the non-inverting amplifier. As you can probably guess, this one boosts the signal but keeps it the right way up. The gain is still set by 2 resistors, and it's always going to be a number greater than 1. This is the circuit you'd reach for when you need a stronger signal, but you don't want to flip its polarity.
So what happens if we go back and just remove the feedback entirely? What if we unleash that massive raw gain? Well, then you get a comparator. This circuit is basically a decision maker. It just compares the two input voltages and slams its output all the way high or all the way low, depending on which one is bigger. It's how you get a simple, digital, yes or no answer from an analog signal.
So you're probably realizing how useful these are, but here's the thing. There are literally thousands of different op-amps out there. Each one is a little different. So with all those choices, how in the world do you pick the right one for your project? Let's walk through a simple way to figure it out.
It really just comes down to asking yourself 4 key questions. First, what's my voltage range? You've got to make sure the op-amp can even run on your power supply. Second, how fast is my signal? This is where you look at the gain bandwidth product on the datasheet to see if it can keep up. Third, what's my power budget? If you're building something battery-powered, you want something with a low quiescent current. And finally, number 4, how accurate do I need to be? For really precise measurements, you'll need to find one with a low input offset voltage.
From building audio filters and guitar amps to making super precise sensor circuits and robot control systems, the op-amp is a true fundamental building block, just waiting for your ideas. So now that you know its secrets, the only real question left is, what are you going to build with it?